IITians Hub to this first session for your 2-year integrated JEE program, and wish you all the very best in the coming 2 years. You may achieve your goals of IITs or getting into the top engineering colleges. Okay. It has been a difficult time, I know, for all of you in the last year or so, coping with the situation of lockdown and pandemic, and apart from the fact that it is frustrating to be studying from home, not being able to interact with your teachers, interact with your friends, not being able to have normal activities like sports, etc. Apart from that frustration itself, there are a lot of families who are affected by the COVID pandemic in a more direct way, and sincerely, I hope that all of you are coping well with that situation. Okay. Now, we have now reached a situation where we really have to try and have a positive outlook, okay, and look ahead to the future. Whatever our losses because of the pandemic, whether it is a personal loss or it is a matter of the frustration of not being able to have a normal life for so many months, we have to put that behind us. Okay? And in a situation where the board exams have got cancelled, more or less, okay, we are now in a position to be able to start our journey for the next priority, which is the biggest priority of our lives, which is the engineering entrance exams in your 2023 year. So in that respect, we are starting this course at the very appropriate time, at a very correct time. You will have no loss in terms of your academics when it comes to your entrance exam preparation, and in that sense, it is very good. So for many of you who probably do not know me, haven't met me before, let me start by introducing myself. My name is Shom Bhattacharya. I'm writing the name here. And I'll be one of your physics faculties for the next 2 years. Okay. So today's lecture, we will not begin any real topic in physics. We will just speak about a few general things, understand each other. But before we start the actual lecture, let me just explain to you the protocol of the online lectures. Okay. I see that we still have a couple of students joining in. Anyway, so the first point that I want to make to all of you is that these lectures are going to be recorded. Okay. So at any point of time in the lecture, if you lose connectivity because of internet issues, do not worry, okay, because you will have the recording of the lecture at a later stage to go through, and you can cover up the portion that you might have missed because of connectivity issues. Okay. But at the same time, just because the lecture is recorded, don't take it casually. Like, be very alert during the lecture. Treat it like a normal face-to-face lecture. And of course, we will be having the normal physical lectures also as soon as possible. While the pandemic is still going on and we are in a very grim situation, but there is light at the end of the tunnel. There is a lot of hope for us because, as you know, from 1st of May, the vaccination process is starting for 18+ people, and then very soon after that, the vaccination should be for people younger than that also. And once I think the vaccination process is completed, gradually we will get back to normal life, and that includes physical lectures. Okay. But in the meantime, we are having these online lectures, and let me assure you that in our system of online lectures, we have been very effective with our students, both of class 11th last year, those who are going to class 12th now, and class 12th, those who are giving the JEE exams this year. Students have given the JEE Mains exams in February and March, and they have scored in the same kind of range as students have scored in the previous years. So we assure you that the online lectures are effective, provided students are equally committed. So few of the things about how to make sure that the online lectures are very effective for you, as I told you. First of all, you have to treat them like the regular lectures. Okay. In general, you should have pen and paper with you while you are attending the lecture, and you should write down some brief notes. And when we get on with the syllabus, each lecture will also have a lot of class examples, questions, etc. that we'll be solving during the lecture. Okay, and sometimes actually many a time during the lecture, the teacher will be giving you some problems to solve, give you a bit of time with some explanation, and you have to try and solve those questions, and then those questions will be explained. So that process has to be taken very seriously by you. So first of all, the the attention span during the class. Okay, make sure that you are doing some pen work along with listening to the lecture. Okay, that's very important. If you have any doubt or anything you want to clarify during the lecture, please do not hesitate. Okay, in general you should never hesitate, but especially now because it is an online class, you should not feel hesitant in any way. There are two ways in which you can discuss any query or ask any question during the class. One is that you can send a text message. Okay, so I will just send a message to show all of you how that works. Okay, right. So just like you can see, you would have received a text message from me. So like that, you can send me a message at any point of time of the lecture. So while we are learning something, if you have some question, the first option that you have is to send a text message, and I or any teacher will reply to your query with that. The second option is that you can raise your hand. Okay, you know the icon for raising your hand, and you can unmute yourself. Okay, so the setting in general is such that you should keep yourself at on mute at most of the times. Okay, but when you want to speak something, when you want to ask a question, you should raise your hand and unmute yourself, especially if you have a speaker, and I mean, if you have a microphone and everything, which I'm sure you have. Okay. So that way you can discuss the questions in voice with us. Okay. So those are the two methods of discussing questions. Okay. Now, the other thing which is very important for your online lectures to be effective is that once you have attended the lecture, you've written down the class notes, you have solved any questions that were being done in class. Okay, and you have also discussed any questions and doubts you might have had during the lecture. Now the next part is extremely important, that you should revise your class notes very carefully. And when I say revise your class notes, again it means some kind of pen work, because almost every lecture will involve certain numerical part, whether it is physics, chemistry, or maths, solving of certain questions. So if you do the key steps once again on pen and paper while you're revising it, you will see that your learning will be much faster. Okay. Generally, we always feel a little bit hesitant or lazy to do pen work. It is a natural human instinct. But as you go along in class 11th, you will realize that pen work actually makes things easier for you, makes life easier, because anything that we write down or anything that we solve on pen and paper in terms of mathematical steps, our learning in that is much faster compared to if we were just trying to read it alone. Okay, so actually by doing pen work, you save yourself time in learning and in understanding. So for most people, other than few very gifted people who have photographic memories, and those are, believe me, people with photographic memories are like a handful in lakhs. Okay, so unless you are in that category, it is always going to help you to write down something which you have to remember compared to just reading it again and again. It is a more efficient and faster way of both learning as well as remembering things. Okay. So this is the basic thing. Now there are going to be a lot of other things like regular tests and how to prepare for them and all that. But I will not bore you with all these things today because it's the first day, and I don't want to have a long bhashan baji kind of lecture here. So we will learn about those things more as we go along, and I'm sure all of you have queries about the JEE exam and the pattern of it and all that also. But we will come to those things progressively. Okay, I'm more eager, being a physics person myself. Okay, being a perpetual student of physics myself. also myself every so I really am eager to go ahead with the physics portion of today's session. So let us begin with that. So today is an introductory lecture and we will talk about some general things in physics rather than any particular topic. Eventually, I will also tell you the sequence of topics we will be doing, etc. and all that. But before all that, I would like to start with general discussion. Okay. So what is physics? Okay. If you wanted to describe to a lay person who's not very familiar with the sciences, okay, what is the subject of physics about? Can any of you tell me, like, what in 1 or 2 lines, what is the easiest way to describe that? What does physics deal with? What is the subject about? You can send me text messages. Yeah, tell me, beta.
Sandy here.
Yes.
So physics is basically the math involved behind the working of real world things.
Okay, very good. So nice definition. Anything else, Sanvi, you added? So one reply I've got is that it is about the mathematics.
So
Yeah, just a moment. Of the working of what was it, Sanvi, again? Real world processes,
Objects.
right?
Yes, sir.
Objects. Okay. Real world objects or processes. Okay. Can you give me an example, Sanvi? Yeah, I'll come back to you, beta.
A ball going up, the water being pulled up in a well, small things.
Right. Okay, very good. So, for example, free fall of an object, right? Ball going down.
Yes, sir.
Okay. Then you have the process of water being pulled up from a well. Okay. Very good, Sanvi. There was another person, another student who was saying something. I did not catch the name. Yeah, can you unmute yourself?
yes, sir. Can I say?
Yeah, Anand, tell me. Yeah, good morning, Anand. Tell me.
Yes, sir. So for me, physics is like a nature, means a study of a basic law of nature, like a repetition of day and night and cycle of seasons.
Okay, so it is a study of natural phenomena, you can say, you know?
Yes, so natural phenomena of physical world.
Very good. Of physical world. Okay. So there are some words we are using here, which might be a little bit technical. So let's explain these words. Okay. So what do we understand by the term natural actually?
Nature.
So basically something which is not artificial, right? Not man-made. Yeah, that
Things
is
that
what you
work
say.
independently.
Okay. But then let me just ask you one thing. What is the opposite of natural?
Artificial.
Artificial. Okay. So artificial phenomena, do they involve physics or not?
Yes.
They do.
They also involve physics. Okay. So yeah, it's correct to say that we do study natural phenomena in physics. Okay. But my only point is we don't study only natural phenomena. Okay. Even artificial phenomena are part of the study of physics. Okay. Now, just for clarity, what is the meaning of the term phenomena? In fact, the word here should be natural phenomena, right? Which is the plural of phenomenon. Okay. So what is the meaning of the term phenomena or phenomenon? It's just a very fancy word for any event or happening.
Occurrence.
Occurrence, correct? Huh? This is the plural of phenomenon. And phenomenon just means any event or occurrence Very good. So, physics covers this portion, which is the natural phenomena that we are seeing. Now we come to another interesting term, physical world. Okay. Now, why we have used the term physical over here? That means, we are doing some classification of the natural phenomena. No? We are talking about certain phenomena which fall within the category of physical world. So what exactly we mean by the term physical world, or I might say physical phenomena? What is the meaning of this term? What does the term physical hold over here?
A world that follows physics.
Yeah, but then very nice, Daksh. But then that is circular logic, na? It is like a lawyer. That physics is about physical phenomena. What is physical phenomena? It is about physics. Acha, do you know the quantity? Do you know the term physical quantity?
Yes, sir.
Anything
Yes,
All
sir.
of us have heard of the term physical quantity, na? What is a physical quantity?
any quantity that can be measured.
Very good. Na? Quantity is a more general definition, but a physical quantity is something that can be measured. It is a quantity that can be measured. Okay. So now let's come to what is physical phenomena or the physical world. Physical phenomena are phenomena, as we have seen, are events. Okay. But these are events involving physical quantities affecting each other. Okay. So these involve physical quantities. That means quantities that can be measured affecting each other. Okay. So if we go back to our earlier example, the free fall of a body, okay, that involves basically what? It involves displacement. That is a measurable quantity. Okay, it involves velocity. Okay, it involves acceleration. That acceleration is coming due to gravity, which is the pull of the earth. So all these things are things that we can measure. Okay, and therefore this event, the free fall of a body, comes in the category of what we can call physical phenomena. It comes under the category of physical phenomena because it is these kind of physical quantities which are affecting each other. Time, the amount of time for which it is falling will determine the displacement, the velocity, but it will also be affected by gravity. For example, if the free fall is happening on the Earth's surface, it will have a certain displacement in certain amount of time, certain velocity after certain amount of time. But if the same object was in free fall on the moon's surface or any other planet's surface, then for the same amount of time, it would have a different displacement. Why? Because one physical quantity, that is displacement, is affected by another physical quantity, which is the gravity of the planet or the gravity of the body on which, the heavenly body on which the object is falling, etc. So it is how to relate different physical quantities which are affecting each other. Okay, that kind of study you can say is part of what we do in physics. Okay, now we are also using the term world over here, the physical world. I would like to extend this to something more general and see if you agree with me. We can say physical universe, right?
Yes.
Because
Yes, sir.
things that we study in physics go very much beyond our human experience of the earth. And today, thanks to the study of physics, our knowledge and our understanding of the things around us go far beyond our earth. Even like non-science students are aware, or non-science people are aware thanks to popular science that they read, or thanks to media or books, etc. That there is like not only a solar system around us, but there is a galaxy that we exist in, and there are system of galaxies in the universe. And in fact, many people believe that there are parallel universes. There may or may not be scientific evidence of that. So I don't know how much of you are into how many of you are into science fiction and things like that. But yes, there is a possibility that there are parallel universes that exist in which there are duplicates of all of us who have alternate parallel realities and things like that. So things become pretty complex when we get into cosmology and things like that. Okay, so that's the thing. Okay, anybody else wants to contribute something? I'm just going through your messages. I will post what is there. Yeah, Ishita has posted the same thing, that it is the study of natural phenomena. Okay, Siddharth has also posted that it is the study of nature and its laws. Okay. Nature and its laws is correct, but we will have to be a little bit more specific when we say nature and its laws. For example, even a subject like biology involves a lot of natural phenomena. In fact, a lot of physical phenomena which falls within the natural world. But we do separate biology from physics. Okay. Incidentally, there is a whole suggestion going on in the scientific world right now that biology and physics should not be treated in future like separate natural sciences. They should be combined because they affect each other. So how a cell progresses, or how biological phenomena happen, like evolution of cells, growth of cells, the energy part, how the mitochondria evolves in a cell, and how that affects the progress of the cell. Simple things like mitosis. So everything in the biological world, from simple cell level right up to more complex things like neuroscience, and understanding the nervous system, and how essentially electrical impulses flow through our nervous system, or any organisms which has an evolved brain and nervous system, animals basically. Okay. So even that understanding, it is to do with physical phenomena, and ultimately when we get into the study of that, we are dealing with physics. So at the higher reaches of biology, for example, today there are suggestions of trying to understand brain activity through the interaction with neutrinos, which are extremely small particles, and which are basically to do with particle physics. So there is a confluence between the natural science of biology and the natural science of physics that is taking place more and more. And therefore, people who are doing research in that area have to have a sound knowledge of both the parts, physics as well as biology. So there is an increasing call among the scientific community that these sciences should be combined. So anyhow, so I'm just trying to explain that when we talk about the natural world around us, or the natural physical world around us, there is actually no foundation. Physics deals with everything. Right. Anybody would like to contribute anything else? I see here that Daksh is also sending me a message. I'll come to that. Anybody else would like to speak something, please? Okay, so I have some very nice thoughts over your messages here. I'll just share them with everybody. So Daksh has contributed that it also helps to understand other worldly objects and phenomena, which is true about physics very much. Harshit has contributed that biology is applied chemistry, whereas chemistry is applied physics. Okay, so that's a very interesting thought. So biology is applied chemistry. Okay, Harshit, if you're can you speak, like you have a microphone?
Yes, sir.
Yeah. So can you tell me a little bit more about this statement? It's very interesting. Biology is applied chemistry.
Yes, sir. For example, we know like because of chemistry, things like osmosis happens because of the relation between the different
Right.
atoms and the elements. So in biology, osmosis is seen in plants. It is seen in many cellular levels. So it is just
Yes.
applied chemistry.
Right. And what about the second part of the statement, that whereas chemistry is applied physics?
So this is basically we know the physics of uh, smaller entities like atoms and protons and electrons. Chemistry is just a study of those smaller entities.
Okay, very, very good. So Harshit has brought us to another very important point, that how chemistry and physics are interconnected. Okay, and so therefore it is all interconnected. So just to elaborate a little bit on Harshit's point. See, chemistry is basically the study of how matter reacts with matter, right? It is all to do with properties of atoms and molecules when it comes to how they behave when they are brought in contact with each other. Okay, at the molecular or at the atomic level. So one of the fundamental aspects of chemistry is to understand the structure of the atom. Okay, and from that to understand the behavior of different types of atoms. For example, we know that certain types of atoms have electropositive nature, certain have electronegative nature. You would have heard these things in chemistry. They have different valencies. They might tend to create what is called ionic bonds with certain other atoms. They might tend to create covalent bonds in other situations. Okay, they might be amorphous. They might be crystalline. They might tend to have fluid structure, so on and so forth. We have very interesting things like, for example, we observe something called, in the case of H2O or water, we observe a very strange phenomena called anomalous expansion, which is that when water cools down from 4 degrees C to 0 degrees C, instead of expanding, instead of contracting, which is the normal situation for any material as you're reducing the temperature. In the case of water, from 4 degrees C to 0 degrees C, it expands. Now, up to 4 degrees C, it will contract, but then it expands. And that, for example, happens at the molecular level because of a very interesting phenomena called the hydrogen bonding. Okay. So now when it comes to all these things, interaction between atoms or molecules or bonds and all that, it is like Harshit has suggested, it is nothing but physics. Okay. And at an even more fundamental level, when we are studying the properties of an atom, and from those properties, we are trying to understand how that atom, or how the atom for a particular element, which is, a cluster of atoms which all have the same structure, uh, how they will behave in a reaction context. When we are trying to understand that, we come down to structure of the atom, and structure of the atom and properties of the atom are all to do with, as you know, the electronic structure. That is the how the electrons, okay, are distributed in the orbits around the nucleus. So when we come to that, we'll come to a very interesting discussion which we'll have later today, which is about electrostatics, right? The type of interaction that happened between charged particles. So as all of you know, that there are fundamental particles, subatomic particles, namely proton, electron, and neutron, which are the most important ones. Okay? Protons and neutrons together provide most of the mass of an atom, right? Protons are positively charged and electrons are negatively charged. But the chemical properties of an atom are completely determined by the electronic structure. That is, they are determined by the kind of interaction or the kind of attractive forces that exist between the electrons in orbit with respect to the nucleus, which has the positive charge and which has the protons and neutrons. So now notice that the moment I'm coming down to that, we are talking about things like forces. We are talking about electrostatic interaction. We will at a later stage be talking about potential energy or electrostatic energy. So already we are coming down to the domain of physics, because these are common words in physics: force, energy, interaction, etc. So ultimately, the structure of atom is completely described by the physics of the atom. And that is why you can say that the physics is at the heart of chemistry. Like whatever we study in chemistry as, chemical phenomena, natural phenomena in the domain of chemical reactions, you can say the root cause behind that, okay, or the mechanism behind that is something that you will study by applying physics to it. So it is very true that it is connected. Okay, Soham has also contributed that it is the study of matter and fundamental quantities, very true. And Udit has also contributed that it is studying of objects ranging from too small to too big. So this is a very interesting observation. And this is also something that I want to bring to your light, that is about the range of physics. When we say it deals with physical phenomena in the universe around us, we are actually covering a very huge amount of ground. Okay, we are covering ground from the tiniest of things that are known to mankind to the largest of things that we can imagine. Okay, I can't say they are known to mankind because we experience them more through imagination and study. So the other thing which is important is, because physics deals with, so we can say that physics is a study of the physical universe. And everything in it, right? So by study of the physical universe, we mean that it is all physical phenomena in the universe. So it has a very vast range. So the range of physics is very vast. So we will talk about some of the branches of physics also. But I will start this discussion by initiating you with the domain of particle physics. In particle physics, as you might have heard, we are dealing with the smallest of small things. Okay, so it deals with the fundamental particles of nature. Okay, or the physical universe. So these are extremely small. Okay, so we'll come back to this. And on the other side of the range of physics, we have cosmology, okay, or we have astrophysics, where we are dealing with galaxies, okay, the cosmos, which is basically another word of the for the universe. So we have tremendous amount of range, in the sense that when we talk about the cosmos or universe, we're talking about very large distances. Okay, we are talking about things like black holes, okay, novas, supernovas. But moreover, we are talking about the entire cosmos, which consists of billions and billions, literally uncountable number of galaxies. Okay, so we are talking about very huge distances. Just to understand the kind of range involved over here, a common unit of distance in cosmology or astrophysics. Can you tell me what is the most common unit of distance?
Light
Light
years.
year.
Yes,
Light
very,
year.
very good. So it is light year. Now, when I think about the term light year only, when I first encountered the term light year, I literally went crazy because it's something very extraordinary. Can you tell me what is a light year? What is the definition of light year?
Distance traveled by light in 1 year into the
Okay,
space.
correct. So it is the distance traveled by light in one calendar year, right? So can you imagine what that distance is? Light travels at how much? 3 lakh kilometers per second, right? So speed of light is 3 into 10 raised power 8 meters per second. Okay, or we can say it is 3 lakh kilometers per second, roughly, right? So in 1 year, the amount of distance it will travel is 365 days into 24 hours, okay, into 60 seconds, okay, multiplied by 3 into 10 raised power 8 meters. So this much in meters. It's a staggering amount of distance if you talk about it. And as you know, light year is a relatively small distance when it comes to cosmology, right? We have galaxies which are literally millions of light years away. Okay, so can you imagine million light years means this number multiplied by 10 raised power 6. So it literally means that it takes light a million years to travel from one galaxy to the other. So we are talking about, a system which is a cosmos around us or the universe around us. And when you look into the night sky, or particularly if you look through a telescope or something, you might be seeing a certain star or you might be seeing a certain galaxy, which is, let's say, several light years away. Now, if something is 100 light years away, if the distance of something is 100 light years, the even more interesting thing is that you are seeing back in time. You're seeing 100 years back in time. Is that correct?
Yes,
Can
sir.
anybody can anybody explain this thing which I'm saying? That when I see something which is at a distance of 100 light years, I'm seeing 100 years back in time. Can you explain this?
So
The
this
star
happens.
was 100 years back in this position.
Yeah. Anirudh, go ahead. Then Daksh, you can say after that. Yeah.
So the star was 100 years back in that position because the light has taken 100 years to reach our eyes.
Yes, exactly. Okay. Yeah, Daksh, you wanted to add something?
No, so that was basically it.
Yeah. So that is the
So
point.
like a
Yeah,
supernova.
so that, yeah, like a supernova or a galaxy or a star, if something is 100 light years away, that means what we are seeing today. Okay, seeing is basically what? Receiving light, literally. Light creates, first of all, light is focused by our eye lens, onto our cornea, and it creates a neurological reaction over there which sends impulses to our brain. which gives us the sensation of sight. It processes that data. So literally seeing something is to do with light. Our eyes have to receive the light from something to understand what it is. Okay? And our brain processes the information from images created by that light, and that's how we are able to have the have the sense of vision. It's one of our 5 sensory things anyway. So seeing something which is 100 light years away means that we are receiving light that was emitted by it not today but 100 years back. So imagine if we are seeing a star today in a certain at a certain temperature, at a certain size, in a certain color. Yeah, Anirudh, you have something more to speak, better?
So then new stars would be added every year, sir, because light coming from the behind stars would be coming to our eyes. We will see
Yes, it
new
is true.
stars
In
every
fact,
year.
yes, it is true. In fact, the universe is always evolving. It is expanding also. Okay. Also, the distance between galaxies is going on increasing, and not only new stars and star systems are created, but also stars are constantly evolving also. Okay. Eventually, a star will explode before it annihilates. So it will explode into a supernova. Okay. So stars have various stages in their life. Okay. And the life cycle of stars itself is like millions of years. So when we see something which is 100 light years away, we are actually seeing a star which is 100 years back in its lifetime. Today, what it is, we have no way of knowing. The earliest we will know that what situation the star is in today will be 100 years from now, because it takes light only to 100 years to travel. Now, light, as you know, is the fastest form of information that can travel from one point to another. There's no other way of having information. There's no other communication system that can make information flow faster than the speed of light. So there is simply no way with the existing technology today that we have any information about that star, which is 100 light years away. We don't have any information which is more recent than 100 years. So that is what we mean by saying that if something is at a distance of 100 light years, we are looking back in time. We are looking back in time.
Excuse me, sir.
Oh, yes, beta.
Sir, so you said expanding universe.
Yes.
This term is used a lot. I've seen this in a lot of science videos, but I don't get the concept. If you're saying an expanding universe, do you mean there's something blank beyond it?
Yeah. No, what we mean by it's not exactly that there's something blank beyond it, but there is actually a term in thermodynamics that we will study later, which you would have also heard if you've heard about expanding universe. It is a term called entropy. Have you heard the term entropy, beta?
Yes, sir. Vaguely.
Hmm? Yeah, vaguely. So entropy is it's a very vague concept actually. Okay. Entropy is something to do with chaos, okay, or the degree of disorder. So there is a theory in physics which says that the entropy of everything, in fact, the entropy of the universe has to always increase, because that is the direction in which time goes. Okay. It's the
Okay.
same reason why, it's the same reason why if we open a can of pressurized gas, that gas will very quickly, the gas will very quickly spread out, okay, into the atmospheric air around. Whereas the reverse of that process you will never see happening. Okay, like we cannot suddenly open a can. I mean, we cannot open a vacuumized can and then expect a certain gas from the atmospheric air around us, like nitrogen or oxygen, to come into the can on its own, pressurize itself, and become liquid. Right? We don't see that happening.
Yes, sir.
Okay, so the reason why events happen in a certain direction in time, that when time is going forward, okay, what we will see is that when we open the can of pressurized gas, that gas will tend to spread out around it. Okay, it will tend to leak and spread in the atmospheric air around, and not the other way around. Okay, or for example, when you stir coffee or tea or whatever in a cup, when you stir a liquid in a cup, you will see that because of the resistive forces like air resistance, friction, viscosity, etc., gradually it the kinetic energy of the molecules become lesser and lesser. Eventually, it becomes still. So technically it's very interesting that if you have a liquid which has been stirred, so the liquid molecules possess a certain amount of kinetic energy. If you keep it in a vacuumized chamber or in a heat sealed chamber, okay, what you will observe is as the liquid slows down and it stops swirling, the temperature will increase slightly because kinetic energy would have converted into heat energy. But the reverse of that doesn't happen. That if you have still liquid in a container, you cannot, without any external force acting on it, you won't observe that it will suddenly start moving because heat energy is converted into kinetic energy. So these are just 2 or 3 examples. Okay, another very simple example would be, something about the concept of zeroth law of thermodynamics, that when I bring a warmer material in contact with a cooler material, we always observe that the one at lower temperature, its temperature will rise. The one at higher temperature, its temperature will decrease. And we say that in general, the heat energy should be conserved. The one which is losing heat, it will lose the same amount of heat as the one which is gaining heat. Okay, so there's a conservation of energy principle over here. But if you really think about it, why the reverse of that cannot happen? Why cannot heat flow from lower temperature to higher temperature? Even then, energy would be conserved. So it is not violating the principle of conservation of energy. But what it would violate is the principle of entropy, that the amount of chaos in our universe, the amount of randomness in our universe is always increasing. It can never decrease. That is the nature of time. That is the direction in which time goes. Time always goes in the forward direction. And as time goes in the forward direction, the entropy of the universe or the chaos in the universe is always increasing. So that is one of the very interesting theories of thermodynamics and in general physics at a higher level. So that says basically that the universe consists of objects of its own, like galaxies, etc., and they are always moving away from each other. So as they are moving away from each other, the outer boundaries of the universe are always expanding.
Okay.
Okay, so it is not like there's no consistent theory that there is some empty space into which the universe is gradually expanding, like the case of gas expanding from a container into the room around it. It's not exactly like that, but you can think of there are many different models of the universe. Like if you get into cosmology, there's something called the liquid drop model of the universe. Now a liquid drop, it has a boundary, right? And that
Yes.
boundary is a little bit flexible, okay, right? So, for example, if a droplet of liquid is in free fall, like rain droplets, right? You generally tend to observe what kind of shape of the droplet. A falling raindrop, okay, it would have typically this kind of shape, slightly ellipsoidal, not
Yes.
perfectly round. Okay. So why that happens? That happens because of gravity acting on it. The shape becomes like this.
Yes, sir.
Okay. Now, do you know what will happen to this droplet of liquid if I take it into space or gravity-free environment? How will its shape be?
Completely circular.
Oh, circular.
Very nice. It will be perfectly spherical. It's three-dimensional, no? So it will not be like an elongated sphere. It will be perfectly spherical. Okay. Now, this itself, if you think about it, is a very curious fact, because this is a symmetrical shape. Okay. Now, how does nature know that it has to adjust itself into a perfectly spherical shape? It's quite curious, no? Like we don't generally see geometrical shapes in nature. No? It's very hard to see something which has a straight line in nature. You will never see a cliff or a tree trunk or something like that which is perfectly straight. Okay, you will never see a rock which is perfectly cuboidal. Okay, or rock which is perfectly spherical. But yet it is very curious that when we take a liquid droplet to a gravity-free environment or an environment where it is not affected by any other force, then it takes a perfect spherical shape. Okay. Now that is something because of, have you heard the term surface tension?
Yes, sir.
Yes, sir.
Yes, sir.
So any idea what is surface tension?
Sir, the resistivity of changing an environment by liquid. Like if you drop a liquid on coin, then it stays on the coin for a minute, and if we continuously drop the liquid
So
on
you are
coin,
saying
and
it
at
has
a
something
point.
to do with the stickiness, no?
Yes, sir.
Something to do with the stickiness of the liquid. Yes, that is one of the, you can say that is one of the repercussions of surface tension. It is the property of surface tension that partly creates the stickiness of a liquid, right? Like if you take a glass rod and dip it into a bowl of water and then remove it, you will see certain droplets of liquid which are sticking onto the glass, right? Another example of surface tensions application, I'll tell you. You can think of this experiment yourself. Okay, you have, let's say, two glass rods, okay, which I'm just showing like this. Now you keep them very close to each other. So this is one glass rod and there's another glass rod. You kept them almost in contact with each other like this. Okay. Then you take some liquid which has typically high amount of surface tension, like soap solution. Okay. Soap, as you know, has sodium stearate, and the stearate ions are very large ions which are, they create the property of stickiness or surface tension. So you put some droplets of soap solution in between these two. Okay. So this is some kind of soap solution. Now very slowly you separate one rod from the other, very slowly and very cautiously. So what you will observe, there'll be a soap solution film in between them, right? Aisa hoga?
Yes, sir.
Of course, at a certain stage, when the distance has reached a certain critical value, that soap's film will tend to break, right? But there will be a soap film. And if you observe this soap film carefully, it has a very interesting property. It might even be sort of oscillating a little bit, like a flexible surface, like a paper surface because of the wind. So this shows now that a liquid surface, basically what is a liquid film? Okay, so this will be a soap film. And I'm sure all of you have, blown into soap films to create soap bubbles. Those are also very interesting phenomena in physics. You can observe refraction of light. You can observe, the whole phenomena of buoyant force and how soap bubbles rise in air because of the phenomena of buoyancy and surface tension, etc. So anyway, so the soap film, if you observe it now, it is very much like a flexible surface. It is like suppose you had a thin piece of rubber, and you had stretched it. So you have a rubber membrane. So the rubber membrane has that property of flexibility. So like that, the soap film surface also has that property of flexibility. And that property of flexibility only is what is surface tension. Okay, you're understanding the point? What is surface tension? So I will not get into the physics definition of surface tension yet. It is something that we'll be studying later, but it has to do with the fact that the surface of a liquid is actually like a elastic material. It is flexible. It is like an elastic material. Okay. Now, all of you know one thing, that any elastic material on its own, how it tends to be. It tends to contract to the minimum value, right? The minimum geometry. Like if you have a rubber band, okay, if you are applying force on it, it is stretched because of its elasticity. But if you release the force, how the rubber band tends to behave? It tends to come to its minimum length, which is its natural length. So why that happens? Because of the phenomena of potential energy or elastic energy. Any elastic material, it has a certain kind of energy called the elastic energy. And the more we stretch it, the more the amount of elastic energy stored in it. Like I think you would have studied in your physics course till now about the elastic energy of a spring. Okay. Or an elastic band, like a rubber band. Elastic band, or just a cord made of elastic material, like a rubber cord. Sorry, the spelling is C-O-R-D, not C-H-O-R-D. I, being a musician also, I tend to always use musical terms anyway. So what you observe about these kind of materials, they have the property of elasticity. So that means that if we apply some force on it, they will tend to change their shape. If we apply external force like this, the spring or this elastic band, it will tend to get stretched. Now, as it tends to get stretched, what is happening is that the force that we are applying, F, is force applied by external agent. Some external agent is applying some kind of force. Now you'll notice that that force is doing work. Okay, because it is displacing. Now, when we start stretching the spring, for example, suppose the spring is attached to a wall like this. Okay, and initially it is at its natural length. Now we start applying a force from this side, and as a result of the application of that force, the spring stretches like this. Okay, so kya ho raha hai? The point where we are applying the force, the point of application of the force is displacing like this. So the work done by that force will be F into S or whatever. So it is doing positive work. So what is happening to this work that it is doing? It is getting stored as elastic energy or potential energy. We can use the term interchangeably, potential energy or elastic energy in the spring. Okay. Now so when you compare the spring in a stretched state versus the spring in its natural state, okay, in this state it is having positive potential energy, it is having positive energy or positive elastic potential energy. So when something has larger amount of energy, it is more unstable. It is an unwritten rule of physics that higher potential energy means more instability, lesser stability. So when we release the external forces, what will happen? It will tend to go back to this. So any system, it tends to lower its energy, its potential energy, and thereby it tends to gain stability. Okay. So whenever we see any elastic material, we might have stretched it by applying external force, and in the process our external force has done work on that, and that work has got stored in the elastic material as elastic potential energy. But on its own, the material will always have a tendency to apply what is called a restorative force. The spring here, even as we are applying the force from both sides, okay, the spring on its own will apply a force which we call tension. We will come to this later in physics. This type of force is called tension. So it will try to apply an internal force of tension, which tries to do what? It's trying to restore the spring back to its natural shape, which is this one. So the moment we remove the external force or we stop applying it, we'll see that the internal force brings it back to this state where it has lower potential energy. It has lower energy, so it has more stability. So it is stable. Whereas here it is having more higher energy, so it is unstable. So like this, any elastic system. So now you go from this to a two-dimensional system. Okay. So instead of a spring or a cord, you just imagine you have a rubber membrane. Like you have a sheet of rubber like this. Okay. Like it might be a square sheet or something. So this has its own sort of geometry. It has its own shape, which is L by L. Now, suppose you start pulling it from various sides. You are applying forces like this. Then it will tend to get stretched. It may even lose its shape. It may not remain square. It might become a rhombus, or it might become like a parallelogram or whatever. Actually a rhombus, because okay. Or maybe you're stretching from one side, so it goes from becoming a square to a rectangle or whatever. Okay, but the moment you do that, you'll realize that there is some potential energy stored in it, and it has some kind of restorative force, some internal force which is trying to restore it back to its natural shape. So the moment you release the external force, it will lower its energy and come back to its natural shape, which is more stable. So the same goes with a liquid's surface. Okay, the surface tension of a liquid is to do with the same property. It is the property because of which a fluid surface has elasticity. Okay. Another very good evidence for this elasticity. Have you people ever seen photographs or videos of insects walking on water?
Yes, sir.
It's a very curious photo, right? Okay. Like you will see that the insect is actually not floating in water because no part of its body is under the water. Okay. So you might observe that on a liquid surface of a pond, there is a tiny insect which is actually walking across without any part of its body under the water. So if there's no part of the body under the water, that means there's no buoyant force on it. So what is balancing its weight? What is balancing its weight? It is the property of surface tension. Or I'll give you a better example of this. You can try this experiment at home. You take a container having water. In fact, it is better to perform this experiment with soap water. Okay, so you take a container having soap water, because soap water has more surface tension. And you take a thin needle, the thinnest gauge needle that you can find at home. You take this. Now you put the needle underwater. You will see it sinks, right? Because it's made of metal. So what information I'm getting from the fact that the metal will sink? What can I tell about the metal?
So the metal has more density than the soap water.
Extremely. That's very good. That's correct. Okay. So the fact that it sinks means that the metal has greater density. So if it has more density, that means its weight will always exceed the upthrust. Right? You're familiar with upthrust or buoyant force, Archimedes principle.
Yes, sir.
So that means a metallic object, a solid metallic object cannot float. Okay. Of course, hollow metallic objects can float. That's a different reason. We'll come to that. Ships are made of metallic hulls only, but they are not solid. They are hollow from inside. So comparatively, their weight, I mean, their average density becomes less because they have cavity inside. Okay. But a solid metallic object simply cannot float because it has this property that its density of the metal is more density than density of water or density of the solution. Okay. But you will observe something, and you might have seen this also. If you place the needle very gently on the surface, you might be able to achieve equilibrium. It might float. It depends on the gauge of the needle. Okay.
Yes, so
Right.
there's this experiment where you put a piece of tissue or something and then you
Yes.
slightly remove it so the needle stays.
Right. So you have to do this very, very gently. And as you correctly said, that is a proper method of doing it. That you float a piece of tissue paper, you place the needle on it, and then very gently you're slowly removing the tissue. So you observe that by the time the tissue is removed, the needle remains there. Okay. So now what can you say scientifically speaking about this? How come the needle is not in free fall? It is not sinking. Definitely buoyancy cannot save you. You're understanding the point now? Because we have already established that buoyancy cannot balance the weight, because when the needle was completely inside water, that is when the buoyancy is maximum, because the buoyant force depends on the amount of submerged volume. No?
Yes, sir.
Right? All of you understanding this point? No? Like if I have a block which is completely submerged in water, the buoyancy acting on it is proportional to its full volume. Whereas if I have it half submerged, then the buoyancy acting on it is proportional to half its volume, because only half is submerged. So when the needle is on the surface, definitely all of it is not submerged. No? So buoyancy on the needle at this point of time is less than the buoyancy when it is completely submerged. So at this point of time, when it's completely submerged, the buoyancy cannot save it from sinking, because mg is greater than the buoyant force. So definitely at this point of time also buoyancy cannot save it when it's on the surface over here. So then what is keeping the needle afloat? You've done the experiment. What is the explanation that was given to you for the experiment?
Surface tension.
Yes, very good. Surface tension. So how you have to visualize it now is that the surface of liquid is like a rubber membrane. Okay, now think of another experiment where you have a thin sheet of rubber which you have kept stretched out onto some kind of frame. So you made some solid frame like frame of wood or something, and you stretched out a rubber sheet, and you stretched it out and nailed it onto the wood. So it is in that stretched kind of state. So normally, because its weight is very less, it will tend to be flat. The surface will tend to be flat. But if you keep some object on the surface over here, it will depress it. So what will happen is the side view of the rubber sheet, would be flat like this without any object. But when you place some object on it, it will tend to get slightly depressed where the object is present. Okay. And where it gets depressed where the object is present, what is happening is the stretch in the rubber, okay, that is creating a restorative force like this. Okay, just like the stretch in the spring creates a tension, the stretch in that membrane also creates a tension like this. So these two tensions which are acting at some angle like this, we will be learning vectors very soon, and we'll understand how exactly the maths of this works. But it's easy to understand that on an object, if you apply two forces like this, they tend to create a net force in the upward direction, right? Right. So this is clear,
Yes,
people?
sir.
So this surface tension, so this tension that is acting, this is because of the elasticity of the rubber membrane, or it is because of the, so in this case we are talking about a rubber membrane. We'll come back to the example of the liquid surface also. So the rubber membrane here is at its natural shape, but when we kept the object on it, it is stretched. So the moment it is stretched, it has elastic force, which we'll call the tension T. So anything kept in contact with it will also experience that kind of reactionary force, and its weight is getting balanced by this. So actually in the case of the needle, the same thing is happening, but instead of the rubber membrane, it is the liquid molecules which are at the surface. Okay, they are stuck to each other because of the what is actually called the cohesive forces. You might have heard the term cohesive force and adhesive force.
Yes, sir.
Yes, sir.
So what is cohesive force? It is the force between like molecules, right? And what is adhesive force? It is the force between unlike molecules. Okay. So for example, when liquid droplets stick to your glass rod, like the first experiment we are talking about of surface tension, droplets of soap solution were sticking to the glass rod. They were sticking to the glass rod because of adhesive forces, because there is strong adhesive force between the glass molecules and the liquid molecules. Okay, but when you start to separate the two glass rods, the liquid forms a film, because the liquid molecules are also sticking to each other. They are not only sticking to the glass rods, but they are also sticking to each other, and that is the cohesive force. And that cohesive force only creates the film of liquid. And on the film of liquid, now there is a sort of elasticity because of these cohesive forces only. So cohesive force at the surface of a liquid, that is what creates the property of surface tension. Which creates the property of the elasticity of a surface. And the elasticity of the surface only is basically what keeps that needle in equilibrium. So coming back to our earlier thing, okay, so suppose this was our glass container in which we have kept soap solution. Okay. Now where we place the needle now, you will see that the surface has actually become slightly depressed. The surface has become contoured like this. So if I see a very magnified side view of the needle, so now think that I'm magnifying this diagram many times, and I'm seeing the needle from its length on. So I'll see it like the cross section of a tiny cylinder. Okay. The length is going into the plane. So in the three-dimensional diagram, the magnified diagram of the needle is like this. But I'm seeing it from side on. So that is this diagram. So there I will see that the surface of liquid where the needle is present has got slightly depressed like this. So that depression of that surface is creating an elastic force. And that elastic force, which is actually now called surface tensional force, that is what is balancing the weight of the liquid. And in fact, few years back in JEE, there was a question which was exactly based on this diagram. The value of surface tension, the length of the needle, the density of the needle, all this was given. And we had to calculate the angle by which the liquid gets depressed over there. So this is actually related to our JEE syllabus. We'll be studying about these things later. So anyhow, so through this example, what I'm showing you is that a liquid surface has the property of elasticity. It actually acts like an elastic membrane. So now coming back to where I started this discussion from, it was about the universe and our thoughts that the universe is expanding, what that means. So one of the models of the universe, you might have heard this term also, since you have heard so many terms, you might have seen this also. It is called the liquid drop model. Have you heard this term ever? Okay, otherwise you can look it up on later. Okay, it is called the, I mean, it's a term from cosmology, so it doesn't really come in your syllabus yet, but it is called the liquid drop model of the universe. So in this model, what it is thought of is that the universe itself is like a droplet of liquid, obviously a very huge droplet. Okay, so the outer boundary of the universe, it has elasticity. It is elastic in nature. So then whatever is inside in the universe, that is our galaxies, okay, their entropy is always increasing. So as their entropy is increasing, because of the elastic nature of the boundary, the universe is always expanding. Okay, so this was the starting point of our discussion. That's how I got into, from cosmology and galaxies and light years, how I got into the discussion about surface tension. And that is the interesting thing about physics, that you can start from somewhere and reach altogether at a different part of physics. But later you will see how they are interconnected, right? So this point is clear with us here?
Yes, sir.
Right? So one,
Yes.
so to a certain extent, this will give you a feel about, why the universe is, how it is able to expand, because the outer boundaries of the universe, they are in this particular model, they can be treated like a film of liquid. Okay, or the entire universe's structure is like a liquid drop. So as the entropy of all the systems within that droplet are increasing, the outer boundaries will get more and more stretched. Okay, and that has to do with the law of entropy also, that entropy of the universe is always increasing. Okay, right, so we'll continue ahead, but before that, I think okay, yeah, Maitri, you had a question, beta, how it will remain stable? Sorry, I missed the question earlier.
No, sir, it's about the liquid drop model only.
So how it remains stable now? It is like this, that see, the thing is, at a very simple level, when we are talking about a spring, let's think of it like this, that suppose we have a spring which is between a wall and another object. Okay, now this object is also like this. Okay, now right now let's say the spring is in natural length. Okay, now let us say this is a metallic block and these are concrete walls, both of these. Now suppose I raise the temperature of this system, what will tend to happen? The concrete walls will hardly move, because thermal expansion of concrete is negligible, right, beta?
Metal block will.
Yes. So if I raise the temperature, what will happen is the metallic block will expand. It will respond more to the temperature change compared to the concrete. Okay. So as a result of that, what will happen to the spring? It will compress. Okay. But as long as I am keeping the temperature higher, the spring will be stable in its new position. Why?
Yes,
because
sir.
because I have stored energy, thermal energy, into the metallic block by raising its temperature, and in the process that has done work on the spring and it stored potential energy on the spring also. So till I release that energy over here, the spring will also be stable in its new position of compression. Okay, it's only when I release the energy, the thermal energy from the block, then the spring will tend to expand back. So same way in the universe, what is happening? The entropy of the materials inside the liquid drop, or basically the entropy of the entire universe, it's increasing because of thermodynamics. So that is causing its outer boundary to stretch and reach a new stability. It's only if I reduce the entropy again, it will come back to its original position to reduce its potential energy further.
Okay,
Right?
sir.
So I hope it is somewhat clear, because there's a lot more technicality in this, but yeah. Daksh, you had a question, beta?
Yes, sir. I had actually two. Sir, does this mean that there's an end to the universe? Like there's a boundary which keeps expanding, right? There's somewhere the universe ends, at least for some time.
Yes, there is a prediction that there is a lifetime of everything in the universe, and therefore the universe also. Like as you know that the sun also has, like our solar system sun, it has a lifetime, though it's like billions of years. Okay, like that our galaxies also have some lifetime. So accordingly, the universe should also have some predicted kind of lifetime. No?
So it can happen that it will snap back.
Yes, it can happen, but luckily for us, like it's not going to fall anywhere close to like the Earth's lifetime is much shorter compared to the sun's lifetime. You know?
Yeah.
So natural life on Earth will cease to exist at a much earlier date compared to when the Earth will cease to exist, and so on and so forth.
Okay.
Right. Okay, so we don't have to worry about that because it's billions of years. So, but yes, there is currently in cosmology, I don't think there is any accurate way of predicting the lifetime of the universe. There are accurate ways of predicting the lifetime of stars when they will explode into supernovas and then contract into white dwarfs and things like that. There are ways of estimating that. Okay, but for the universe, there is no predicted lifetime. Okay.
Okay.
Parv, sorry, Parv, you had a question, beta?
Yes, sir.
Yeah.
In this example of that metallic block and spring, the spring, what is the material of the spring like used?
The spring is also metallic, beta. Typically, a
So
spring is
won't
made of
that
metallic
expand?
material. Yes, the metal of the spring will also tend to expand, which is why its potential energy will be further more. Okay, because the natural length of the spring at the higher temperature is even more than L. Okay, whereas here the compressed length of the spring is L minus X. No? So you're understanding my point, beta?
No.
Okay, I'll explain again. So suppose I'm looking at a spring at 25 degrees C. Okay, at 25 degrees C, the natural length of the spring is L1. Okay, now the same spring, if I look at it at, let's say, 75 degrees C, its natural length will be more. It will be L2. Okay, so now suppose I am keeping this spring forcefully compressed by applying some force on it. Okay, so that its length has become L1 minus X. Okay, now suppose I was doing this at 25 degrees C, then how much is the compression of the spring? The compression is X, because at 25 degrees C, the natural length only is L1. Okay, so far clear, Daksh? Sorry, Parv?
Yes.
Okay, but suppose I'm doing this same experiment at 75 degrees C, and I've kept the length of the spring this much only, L1 minus X. So now what is the compression actually? It is not X, it is more than X, no?
Yes.
Okay, so like for example, if this L1 was 20 centimeters, okay, and this L2 is, let's say, 22 centimeters, okay, and here I'm actually keeping this compressed at 18 centimeters. So if I had done this experiment at 25 degrees C, the compression of the spring would have been 20 minus 18, that is 2 centimeters. Okay, but if I'm doing it here, then the compression of the spring is X prime, which is actually 22 minus 18. So it's as much as 4 centimeters. Okay, so 4 centimeter compression means there is this spring, which is at 75 degrees C, has more potential energy compared to this spring, which is at 25 degrees. Okay, so does that answer your question somewhat?
Yes, sir.
So basically, as a result of that, to expand like this and keep the spring compressed at a higher temperature, the amount of energy that this metallic block has absorbed from its heat source is even more, because even the spring's natural length would have increased at the higher temperature. Okay.
Okay.
Yeah, now I have some more questions. Yeah, okay, beta. So that's this, Parv, this is clear, na, beta?
Yes, sir.
Okay, very good. Yeah, I have a couple of more people who have questions, so I'll deal with that. Then we'll come back to our discussion. So first of all, people, again, let me assure you that, we are not discussing anything in syllabus today. We will start our physics syllabus from the next week onwards. So if I'm jumping between one topic and another, it is more because of my own, what shall I say, my own enthusiasm to have a conversation with you people. Don't get, unnecessarily worried about the content or the syllabus. Okay, it is just to get us started in the language of physics today. We will go very slowly and very systematically when I start the chapter that we will be doing from the next week onwards. Okay, but yes, this is to encourage you to also ask questions and involve yourself in the discussion. So Anand, you have expressed that something is a little bit confusing. Can you unmute yourself and ask me what exactly is the confusion? Then I'll try to clear it.
I'm
Anand Mishra?
confused with entropy.
Okay. So entropy, now beta, you don't need to worry about right now. Okay, entropy is something that we will study in physics at a later stage. But just briefly to explain to you what is entropy. Okay, entropy is, first of all, it is a physical quantity. So it is something that can be measured. Okay, even though it's difficult to define entropy without some background in physics. Okay, but it is a physical quantity. So it is not, for example, a quantity like IQ, okay, or a quantity like sadness or happiness or something, which are non-physical quantities, which we cannot measure. It is very much a quantity that can be measured. It is a physical quantity. Okay, in fact, it is having a unit of joule per degree Kelvin. Okay. So this is a bit of a look ahead. We'll be discussing about this more in thermodynamics. So joule, as you know, is the unit of heat, and Kelvin is the SI unit of temperature. So in fact, entropy is a physical quantity which is expressed in the unit of heat per unit temperature. Okay, but what is the meaning of the quantity entropy? The entropy of a system is related, okay, to its order, or you can say its disorder, or its randomness, how random the system is. Okay, or in physics sometimes it's also called the amount of chaos in the system. Okay, so the entropy is such a thing which is related to how disorderly a system is, how much randomness it has, or how much chaos it has. And the second law of thermodynamics it expresses that entropy of the universe is always increasing.
Sir,
Yes.
how can you have a law over something so arbitrary like chaos or randomness?
Exactly. That is why I said that it is little, it is a bit of an abstract concept. Okay. If we talk about a particular system, then it's easy to make it a little more systematic. But in general, for the universe, it is an abstract concept. Okay. So for example, you have smoke coming out of a chimney. Okay. Now it has what? Suspended particles, right? And that is what you see as the color of the smoke. Now,
Yes.
okay, now here I can describe the randomness of the system, which is basically smoke. The system is smoke, and smoke is basically, what is the important property of smoke? It is the suspended particles within the smoke. Okay, so what do I mean by randomness of the system? It is the randomness of the motion of the particles.
Yes.
Okay, it is the randomness of the motion of the suspended particles. Okay. Now,
So is it
when
related
smoke is
to
being
turbulent or laminar flow?
sorry, beta, come again.
Is it related to turbulent or laminar flow?
Yes, it can be related to turbulent and laminar flow also to a certain extent. Yes. So laminar flow, or even for that matter steady flow, has a lot less randomness compared to turbulent flow, which has more randomness. Okay, so the moment we subject something to natural forces, it tends to go towards randomness. So the moment we subject something to huge amount of pressure differences and all, it will go from laminar flow to turbulent flow. You understanding the point? Okay. All right. So when we talk about this particular system, smoke coming out of the chimney, okay, what is happening is that at this position, because of the type of forces and the pressure differences, most of the suspended particles, they have velocities which are typically in the upward direction. Due to collisions, the velocities might be a bit random, but still majority of the particles have velocity in the upward direction. So the system has a certain amount of entropy, which is comparatively less. You understanding now? But the moment the smoke comes out of the, so the moment the smoke comes out of the chimney, now the pressure variation has become different. It is in it's in a uniform pressure field of the atmospheric pressure outside. So the smoke particles, naturally what happens, their velocities distribute more randomly. And that is how the smoke spreads. And that's how you gradually you see that the density of the particles, the suspended particles, is becoming lesser and lesser. So what is the natural tendency of the system? The natural tendency of the system is that the randomness is increasing. Okay, that is the randomness is in terms of the motion of the suspended particles. That is tending to increase. Okay.
Yes, so there is some kind of synchronization between them.
Yes, there is some, you can say it's more like a lack of synchronization. Okay. When it is having lower entropy, there was a synchronization. But as it is becoming more chaotic, that synchronization is going away.
So,
like synchronization is inversely proportional to chaos.
Yeah, you can say that to a certain extent. Okay. But then, of course, there are certain natural phenomena which go against this principle also. Like you would have heard of the term resonance, right?
Yes, sir.
Resonance kya hota hai? Like if you have for example, you can do an experiment like this. You have a string, like a metallic wire, like the string of an instrument, like a guitar or something. Now it is tuned to a certain frequency, that string. That means it can vibrate at certain frequency. Now if you bring a tuning fork of the same frequency around it and you sound this tuning fork, so it's creating sound waves of that frequency, then you will see that this string naturally starts to vibrate. So that is resonance, right? So here you can see that the degree of randomness or disorder between the tuning fork and the string, it actually decreases. They tend to oscillate together. Okay. So in a sense, you can say that if you were concentrating only on the tuning fork and the string as a system, its entropy is decreasing. But notice in second law of thermodynamics, I did not say that entropy of a system has to decrease. I said that the entropy of the universe has to increase all the time. So what is happening is that while these two are oscillating in unison, but there's a lot more happening because of their oscillation. More number of air particles are getting displaced, more number of air particles around them, and the sound created by them is dissipating over a larger space. So overall for the universe, the entropy will still be tending to increase. The level of disorder or chaos will still be tending to increase. Okay, so that's why I say that the concept of entropy is a little bit more abstract. Okay, hope you people are understanding somewhat about entropy, right? Yeah. So that's to answer. Yeah, beta.
So if entropy is randomness, then can you predict entropy?
Yeah. So that is the same question that Daksh also had. Daksh has sent me a question on text that if entropy is a physical quantity, how it can be measured? Okay. So does it have units other than this? Okay. Yes, it is a physical quantity, and depending on the kind of system we are dealing with, we have different ways of measuring it. For example, in thermodynamics, okay, applied to gas, applied to an ideal gas. Have you heard of something called Charles' law and Boyle's law in ideal gas?
No, sir.
Pressure is inversely proportional to volume at constant temperature. This is Boyle's law, no?
Yes, sir. PV,
so
P1,
that kind
P,
of thing. That's called an ideal gas. Right. So for an ideal gas, no, for an ideal gas undergoing a process, undergoing what is called a thermodynamic process. Okay. This will be coming in our syllabus a few months down the line. 4 or 5 months from now, we'll be studying this thing in more detail. So for an ideal gas undergoing a thermodynamic process, okay, we define the change in entropy Okay, we define the change in entropy by a symbol delta S. S is for entropy. That is equal to delta Q divided by T. Okay. So delta Q is heat. Okay. And capital T is temperature. Okay. So I'll just show you a quick demonstration about how the law of entropy helps us understand something very fundamental. Okay. Let's see a very basic example. Now suppose I have two chambers of gas. They are heat insulated chambers of gas. Now this has gas at temperature of 27 degrees C. So that is 300 Kelvin. And this has gas at temperature of, let's say, 127 degrees C. So that is 400 Kelvin. Okay. And these are insulated walls. So no heat can escape or enter like this. Okay. Now what I do is I fix a metallic rod in between them. Okay. I drill a hole through the insulated walls and I have a metallic rod. So the metallic rod is heat conducting in nature. It is a conductor. So heat will flow between them. Okay. Now all of you know which direction heat will flow in. Will heat flow from A to B or B to A?
No, B to A.
B2A.
So we definitely know that heat will flow from B to A, right? And let's say that even the metallic rod, it is insulated from outside like this. So heat is only going to flow from one container to the other. So what we can conclude here from you can say like from common sense, that a certain amount of heat, delta Q heat, will flow, or the proper technical term is that it will conduct from B to A in a certain time, let's say delta T. And obviously you know that you can imagine that we have certain methods of actually measuring this also. Okay, we can measure the temperatures of the gases, and suppose we know the heat capacities and all that, so we can actually measure that how much heat has flown. So now what we are seeing over here, this statement on its own, one way to justify it is conservation of energy. Now the gas which is in container B, it will lose energy because it's losing heat, and exactly that much heat will be gained by the container in B. So there is no overall loss of energy in the universe, right? So this, in one sense, it justifies the principle of conservation of energy. But if I tell you why cannot heat flow from A to B, तभी तो energy conserve होगा. Because A will lose energy, B will gain energy. So all I have to say is that, okay, whatever energy A loses, B has to gain that much energy. But can you state any principle or any reason why that doesn't happen? Unless we place something like a compressor in between these two, which is involving extra energy from an external agent or extra force or something, naturally on its own, heat will only flow from B to A. Yeah. So what is the explanation for that? Why should that happen? Ayush, yes? Okay, unfortunately, Ayush, I'm not able to hear what you're saying. You can send me in text message then.
Sir, how energy will be conserved while going from A to B?
See, what I'm saying is, suppose in the actual situation, 5 joules of heat are going from B to A. So what is happening? B's energy is decreasing by 5 joules. A's energy is increasing by 5 joules. So energy is conserved, right?
Yes, sir.
Now think of the reverse. Now, suppose A say 5 joules of heat flows to B. So for this whole system, is the energy changing? No, no. A's energy will reduce by 5 joules, but B's energy will increase by 5 joules. So overall change in energy is 0, no? So energy is conserved.
Yes, sir.
So if I say that, okay, like I know this cannot happen, but if I say that heat energy is flowing from A to B, am I violating the principle of conservation of energy? Not necessarily. As long as I say that whatever energy A loses, B gains that much, it's not violating the principle of conservation of energy. it must be violating some other principle, but it's not violating the conservation of energy. This point is clear, beta?
Sir.
Okay. Okay, now there are two ways of understanding this. Okay, one is a very intuitive picture at the molecular level. Okay, if I compare the molecules of the gas of B, which is at higher temperature, compared to the molecules of gas of A, which is at lower temperature, is there any particular observation I can make about the motion of the molecules? Anyone?
Yes, sir. The particles in B will more rapidly move.
Yes, very good. No? So I can say that the average kinetic energy of molecules in B will be more compared to the average kinetic energy of molecules in A, right? Now you might say that, okay, that's little difficult to imagine if they are different gases. You know, like if, for example, B has nitrogen gas and A has hydrogen gas. So you might say that no, but or reverse. Suppose B has hydrogen gas and B has nitrogen gas. So B is much lighter, no? Hydrogen gas is much lighter. So even though its temperature is more, how can I guarantee it has more kinetic energy? Actually, I can, but chalo, let's make the question simple for right now. Okay, because we haven't learned all the laws. It'll take us quite some time to come to this. Okay, so let's make things even more simple by saying that A and B have the same gas. So we're not worried about the mass. So if they have the same gas in the same amount of quantity, that means whichever is having more temperature, the molecules will be moving faster. So if they are moving faster, now these molecules, they make collisions with the metallic atoms over here. And these molecules of A, they also make collisions with the metallic molecules over here. So during those collisions, which molecules will be giving more energy? The ones which are moving faster?
Yes, sir.
That is a natural law of collisions. You can observe that in everyday life. Like if you are playing snooker and you have two snooker balls which are moving and collide with each other, always the one which was moving faster, that will lose energy, and the one which was going slower before the collision, that will gain energy. Okay, so kinetic energy always goes in the direction of higher kinetic energy to lower kinetic energy in the process of collisions. So because these molecules in B were having higher kinetic energy, so as they collide with the metallic molecules here, they will give more energy. And as these collide with the metallic molecules here, they will give less energy. So that collision of gas molecules with the metallic molecules of the rod, what that results in? That results in vibrational kinetic energy of the metallic molecules. Because metal is a solid material, so the molecules cannot move about like they are moving in a gas, but they do vibrate. Now, all materials have kinetic energy for molecules, even solid materials, even crystalline materials, even metallic materials, even amorphous materials. All materials have some kind of molecular kinetic energy, but they're of different degrees, right? And in the case of solids, that motion or that kinetic energy is because of the vibration of the molecules. It's not because of the translation. So now what is happening? The molecules of solid at this end, at B end, they are vibrating faster compared to the molecules at A. Okay. So again, vibration to vibration, the energy that is transferred from molecule to molecule along the solid, that energy is transferring faster in this direction compared to that direction. And that's how ultimately heat energy transfers from here to here. So this is a very intuitive way of understanding it on the basis of what? On the basis of the motion of molecules. Okay, so when we come to thermodynamics, this kind of explanation or this kind of line of logic, it is called the kinetic theory of heat. Kinetic means motion. So heat and the direction of heat flow and the quantity of heat flow and all these things can be explained on the basis of the motion of molecules. And that is called kinetic theory of thermodynamics or kinetic theory of heat. So that is one way to understand, right? This is justifying it, why heat should flow from B to A. Is that correct, people? Okay, so that's one way to understand that the kinetic energy. So why this is happening? Because average kinetic energy of molecules in B is greater than in A. Okay, so therefore, molecule to molecule, okay, energy transfer.
They are same elements, right?
Yeah, this I'm now right now I'm saying that let's keep them same elements. Okay, but even if they're different elements, actually later we'll see the same thing happens. Okay, but the logic for that is a little bit more lengthy, so I'm not getting into that today. So therefore, molecule to molecule, the energy transfer that is happening, okay, that is from A sorry, from B, from the gas molecules in B, okay, through the rod, okay, through to B. Okay, so molecule to molecule, this transfer of energy that is happening, that will happen in such a way that higher kinetic energy molecules lose energy and lower kinetic energy molecules gain energy during collisions. Okay. And that is why heat flows from higher temperature to lower temperature. Temperature of B is greater than temperature of A. So that is one way of justifying it. And this is the way of justifying it using kinetic theory. That is the theory of heat on the basis of motion or kinetics of molecules. Okay. So this is just an overview. Like, don't worry too much about the details here, because we'll be learning a lot of physics before we get into the proper mathematical equations and all this for this. But let's also see another explanation of the same thing. Now let's see the explanation on the basis of entropy. Okay, so what we had said about entropy earlier, for an ideal gas, okay, undergoing any thermodynamic process, so a thermodynamic process is one where heat and mechanical work are exchanged. So in this case, only heat is exchanged. There's no mechanical work involved. No, but for example, if your gas chamber has a piston attached to it, there's some gas over here, and there is also an electric heater. So we can supply heat to the gas, and we can also do work on the gas by pushing the piston with a force. So you can exchange both heat as a form of energy as well as mechanical work as a form of mechanical energy into the gas. And as a result of that, you're changing the state of the gas. You're changing its pressure, volume, temperature, etc. So such a process in general is called a thermodynamic process. So for an ideal gas undergoing any thermodynamic process, we define the change in entropy. So the symbol I'll use for entropy is S. Delta S is defined as delta Q by T. Okay, you're not supposed to know this definition right now. We will come to this much later in physics. But since we reached here in our discussions, so I'm just showing that. So how do we explain the earlier phenomena on the basis of this? Okay, so let's see that. So A was initially at a temperature of 300 Kelvin. B was at a temperature of 400 Kelvin. Okay, and delta Q amount of heat went from here to here in time delta T. Okay, so what was happening? The change in entropy of B, okay, is basically what? Minus delta Q divided by temperature of B, because the heat exchange from B is negative, because it is losing heat. Okay, so that is minus delta Q divided by 400 kelvins. This is the change in entropy of B. Now likewise, what is the change in entropy of A? It is plus delta Q divided by T. Right, so just if you take this formula directly from me, application of this formula is giving these two. This is correct, people?
Yes.
Yes, no, this is clear now? Okay. Now, what is happening to the entropy of the surrounding environment? It is not changing. Okay, because these are insulated. So there is no heat exchange with the surrounding. It is all insulated. So heat is only flowing from one to the other. So then, as a result of this process, what I can say about the net entropy change of the whole universe, it is only change in entropy of A plus change in entropy of B. Because the surrounding environment is not exchanging any entropy or exchanging any heat with it, right? So what is that change equal to? That is equal to plus delta Q divided by 300 minus delta Q divided by 400. So it is a positive quantity only, no? So this will become plus delta Q divided by 1200. So delta S net, you can see, is positive. Okay. But whereas if we assume reverse of this, if we assume that delta Q heat flows from A to B, which is obviously not going to happen. This is not reality. But let's assume if this happens, then let's see what will be delta S net. It will be delta S for A plus delta S for B. Now this will be minus delta Q divided by 300. And this will be plus delta Q divided by 400. So this will become minus of delta Q by 1200. So it will become negative. Okay. So that is why I know that this cannot happen. Therefore, I know that this cannot happen. It cannot happen on its own. It cannot happen spontaneously. We can force heat to go from here to here, but then we will have to put a compressor. That is what a compressor does now. Your refrigerator's inner temperature is lesser than the temperature of the environment outside. And yet the compressor pumps out heat from the inner chamber to outside. But it is doing that through a mechanical process. Okay, so still the entropy of the universe is increasing because the entropy change is not only happening between the air inside the refrigerator and the air outside, but the machine involved, the compressor, that also involves a change in entropy. That involves a process where electrical energy is first converted to mechanical energy, and mechanical energy is partly converted into heat. Okay, so understanding the point, people.
Yes, sir.
Okay, so when we talk about entropy as a degree of randomness or chaos, it is a much more abstract concept. But if we specifically talk about entropy in a certain situation, like we talk about entropy in a thermodynamic situation for an ideal gas, then we can define entropy by formula also, and through that we can always show that which type of process will be spontaneous, only that process where entropy change is positive for the universe, and which type of process will never occur spontaneously, one where the entropy change for the universe is negative. So that is why without any compressor attached between two materials, the heat will always tend to flow from higher temperature to lower temperature. It cannot flow in the opposite direction. Okay. So we have come a long way in our discussion. We started with something else and we have reached something else, and entropy is not something within our syllabus just now, but the whole purpose of today's session was just to get us started about a general language of physics. What are the kind of logics that we apply? So that was the point I was discussing. Yeah, I have another message from Caleb here, so I want to discuss that. So entropy in the universe never decreases, and therefore more kinetic energy molecules will go to the lower kinetic energy molecules for more disorder. Yeah, that's true. And Caleb, so what will always happen is that the state of the universe will always go from lower entropy to higher entropy. So in a sense that the chaotic motion of molecules around the universe will tend to always increase. So that is why within the universe, galaxies are always moving further apart. Okay. And that is why you always have situations like this, that when you have a supernova or an explosion of a star, the hot gases that are coming out of it are moving further and further away from it. So it's all the time in a situation where the chaotic part of the universe is structured. The chaos in it is always increasing. The disorder in it is always increasing. Hope that is clear, Caleb.
Yes, sir.
Okay. Now coming back to my earlier thing, we were talking about the range of physics. Okay, so in the range of physics, we saw that on the one end we have particle physics, which deals with the smallest of things, and we haven't even started discussing about that today. But I'm sure you are aware of some of the terminology involved in particle physics. Like some of the smallest particles known in physics today are neutrinos, okay, Higgs boson, okay, etc. And they are very, very small. Yeah, quarks. Okay, they are so small that they are governed by a different set of principles called quantum mechanics. We will get to quantum mechanics at a much later stage. Quantum mechanics is a strange set of principles which are very interesting. We'll discuss later. On the other side, we have cosmology, okay, which deals with something very large. But the most important thing is physics deals with everything in between, each and everything in between. So, whether we are talking about, mechanical systems, like machines, okay, etc. Or we are talking about thermodynamics, which includes thermochemistry. Or let's say we are talking about atomic physics, which has to do with the structure of the atom. Or we are talking about something even smaller. We are talking about nuclear physics, what happens inside the nucleus. Okay. Whether we are talking about electromagnetism, okay, we're talking about sound and waves. We're talking about waves includes light, because as you might have heard, light is a wave phenomena. Visible light, okay, ultraviolet, infrared, these are all examples of what we call electromagnetic waves. All this is part of physics. This is all the range of physics and more things are also there in physics. Okay, so that is the interesting thing about physics. So when we talk about the entire range of the physical universe around us, from the smallest of small things which are dealt with in particle physics, to the largest of things that we can imagine, which are part of cosmology, it covers everything in between. All physical processes, all physical phenomena, all natural phenomena which are affecting physical quantities with respect to each other, they all come within the range of, okay. So, for example, in our class 11th syllabus, we will be studying in mechanics, mechanical systems. So mechanical systems we'll be explaining on the basis of force, okay, that is Newton's laws. Then we'll be explaining on the basis of work energy, that is the relation between kinetic energy, potential energy, and work done by forces, etc. Okay. Then through that, we will understand the concept of linear momentum. Okay, so we will study things like collisions, where there is conservation of linear momentum.
So basically all the syllabus of 9th is repeated.
Yeah, but in much more detail. So I'm coming to that also. Okay, then we'll be studying something called rigid body dynamics. So what is rigid body dynamics? So for example, if you take an object like a rod, okay, and you fling it in the air, So what type of motion it has? Its center of mass will go in this type of what is called projectile motion. But as its center of mass is going in that, it might be doing this. It might be also rotating. It's constantly spinning, but at the same time moving also because of gravity. So that's an example of rigid body motion. Okay. Or you have the situation of you have an inclined plane, okay, and you have a cylinder, and the surface of the inclined plane is rough, let's say. So it's got friction. So this is a rough surface. Okay. And this is a solid cylinder. So what happens in the case of the solid cylinder is very interesting. The moment you release it, okay, there is gravity which is pulling it down. Okay. There is a normal contact force which the surface is applying on it. Okay. But as gravity is pulling it down, it has a tendency to slide down like this. Okay. So this point of contact with the ground, that has a tendency of slipping. So the fact that it's a rough surface, there is some friction which acts over here. And as a result of this friction, the object also starts spinning. Okay. Because as you know, on any object, if we apply a force in such a way that that force is acting away from the center of mass, that force creates something called moment. So there is moment of force, or what we will later call as torque. So this torque generates rotation, or it generates angular acceleration. So this friction forces it to rotate like this. So while because of mg and all this, the body has a tendency to slide, but it also has a tendency to rotate. So when you see the cylinder coming down the inclined plane, it has that very interesting type of motion where it is not just translating, that is the center of mass of the cylinder is having a downward velocity. So it's traveling in this direction. So after some time you're seeing the cylinder here, after some time you're seeing the cylinder here, but also about the center of mass there is rotation occurring. So when this kind of rotation occurs along with the linear motion or translation, it is called rolling. So we will learn later that rolling involves a lot less friction compared to sliding. Okay, so that is why if you have a heavy cylinder of mass m on the ground versus a block of mass m on the ground, same mass, it is much easier to push the cylinder. Now you must have experienced this in everyday life. It is much easier to push this compared to this, because this will roll. This will go in such a way that the center of mass moves with velocity and there is rotation about the center of mass, whereas this will slide. It only has motion. So the difference between this and this is that this is a combination of rotation and linear motion. Okay, whereas this one is only linear motion. So understanding all these things, this is all part of rigid body dynamics. Okay. And in rigid body dynamics, this chapter is also called rotational mechanics later. We will be applying all the principles that we have learned earlier. So all these things, the concept of force, the concept of work energy, the concept of linear momentum. Part of linear momentum we will also study is the concept of center of mass. Okay. We'll be studying about this also. So all these concepts together will be applied in this. Okay. Then in addition to this part, so this part is basically what we call the core mechanics part of class 11th. We will also be having part of class 11th, heat and thermodynamics. So in heat and thermodynamics, for example, we will start by things like thermal expansion of materials, which is something you might already be familiar with to a certain extent. Then we'll study about calorimetry, which is also something you studied in 9th, 10th before, specific heat capacity, latent heat, etc. But then we'll be studying about kinetic theory of gases. which will be something new for us. Okay. Then we'll be studying about first law of thermodynamics. Then we'll be studying about application of first law onto heat engines. Okay. This will be the progression. And finally, we'll be studying about heat transfer. The three modes of heat transfer which you've heard about: conduction, convection, and radiation. We were talking about conduction earlier today when we had that metallic rod between the two chambers A and B. Okay, so I'll just take another 2 to 3 minutes to, yeah, Rishabh, I will name the books and all that also. Okay. Yeah, Kaustubh, it's a very interesting reason why cubes cannot roll. Kaustubh has asked the interesting question, why a cube cannot roll. Okay. I will give you a brief explanation, quick one. Okay. See, what happens is, for example, when we put a cube on an inclined plane, that's a very interesting process, and this is a rough inclined plane. Okay, so what happens is the weight of the cube is acting through its center. Okay, so this has what we call a component. So if you don't understand the language of component, do not worry, we will study very soon. So that is giving the cube a tendency to slide like this. Okay, so that will cause friction to act like this. Friction will act at the bottom surface. Okay, it will act like this. So now you can see that this friction is giving it a tendency to rotate like this, but it is not going to rotate. Instead, what will happen? The normal reaction, which was earlier acting through this point, it now acts through this point. Okay, so now when you observe this cube, now on this cube, mg is acting through the center. So mg does not have any torque about the center, so it does not create torque. It does not create any tendency to rotate. But the friction, which is acting like this, it creates torque because it has this moment arm. So it creates torque. So it gives a tendency to rotate like this. But then at the same time, what is happening? We also have the third force of normal reaction. So that takes care of this. It stabilizes the object, doesn't allow it to rotate, because now normal reaction acts like this. The contact force, it shifts its direction so that it acts at a certain distance from the center. So this now creates a torque in the opposite direction. Sorry, normal reaction will shift not in this direction, in the opposite direction. So just a quick correction here. Normal reaction will shift its direction, its line of action to like this. It will start acting closer to this edge. So that will give it a tendency to rotate in the opposite direction. So this and this are cancelling each other. So this now creates, you can see, normal reaction force. This creates now what we call a clockwise torque. Creates a torque like this, whereas this was creating an anti-clockwise torque. Okay, which was like this. So these two cancel each other. So the two torques cancel each other. They adjust in such a way that they cancel each other. But you'll also notice something, that if the inclined plane is too much inclined, if it gets inclined too much, then this will tend to topple. So then it tends to topple because this clockwise torque cannot balance the anti-clockwise torque because of friction. Okay, you are understanding this?
How can you explain it again?
Okay. Okay, so just think like this. Okay. Now see, if you have, let's say, a rod, which is suspended like this through a pin on the wall. Okay. Now what will happen if I apply a force in this direction? It will tend to rotate like this because this force has a moment arm. And you can see that it tends to create a sense of rotation in this direction, force into moment arm. So it creates a torque like this. This force F1 is creating a torque like this. This is clear, beta?
Yes, sir.
Now, similarly, if I apply a force like this will tend to create a torque like this. Okay. So it is always possible to apply two forces in such a way that their torques will balance, so there won't be any rotation. This is clear now?
Yes, sir.
Okay. Now see, next let us look at this situation that suppose I have this block which is on the ground. Now, if you think about the normal reaction force, it is basically what? It is a pressure into area. So the weight of the block is acting through the center of mass. So that is a force that's acting vertically down and it's acting symmetrically. So it creates a uniform pressure over here. So the reaction pressure force is also uniformly distributed. That's correct. Is this all right, Beta?
Yes, sir.
So if this pressure is uniformly distributed, that means the net force is acting through which point? The symmetry point, the midpoint, like this. Okay, na?
Yes, sir.
So there is no rotation here because both the forces are creating zero torque because both of them are acting through the center, right? Okay. Now let's come to the case of the inclined plane. Now on the inclined plane, what is happening? See, the moment I leave the block on the inclined plane, which is rough by the way, remember. Okay. So what is happening? The weight is acting through the center downwards. Okay. So it has a component which is along this direction, parallel to the inclined plane. So that gives this a tendency to slide like this. It starts to slide like this. So the moment it slides like this, there will be a friction that acts over here. Okay. So this friction is giving it a tendency to rotate like this. So clear so far?
Yes, sir.
Okay. Now see, because of this tendency to rotate, if you think about the pressure that this is applying on the floor, is that pressure going to be uniformly distributed now? Nahin, na? It's tending to rotate like this. So this part will apply more pressure. This part will apply less pressure. It is making sense?
Yes, sir.
Yeah, beta, this is clear now?
Yes, sir.
So if the pressure has become non-uniformly distributed, what can I say about the net force because of the pressure? The reaction force that the ground is applying because of the pressure. वो भी ये वाले line से shift हो गया होगा. It would have become like this. Because this side has more pressure.
Yes, sir.
It's action reaction principle, no? So the object is applying force due to pressure like this on the floor. So the floor will also apply equal and opposite. So because the pressure is not uniform anymore. Now this half of the block, to divide the block mentally into two halves, this half is applying more pressure. This half is applying less pressure. So as a reaction force, the normal reaction is also distributed non-uniformly like this. This part is experiencing more force from the ground. This part is experiencing less force from the ground. So the net normal reaction force is line of action has got shifted like this. It's to the left of the center of mass. Is this clear now, Beta?
Yes, sir.
So that's how it is adjusting. So the moment this has adjusted to the left, this one is creating a torque like this. So the torque due to normal reaction is balancing the torque due to friction, and that's not allowing it to topple. That's how this object is not toppling and it's just coming sliding down. Okay, but if I gradually go on increasing the angle of inclination, this will not be able to sustain. At some angle, what will happen? The normal reaction will not be able to create enough torque. So the friction torque will win and it will topple over. So in that case, what will happen is if the inclined plane is too inclined like this, then instead of sliding down, I'll observe this is what
the object would roll.
The object will, yeah. So typically in mechanics, we call that toppling. Okay. And it's a very interesting part. Like, you know, when we come to rigid body mechanics, 3 months or so from now, 3 to 4 months, we'll see that we can do an exact calculation. If we know the amount of friction on the surface, and if we know the exact angle, and we know the dimensions of this block, you know, what is the length, what is the width and all that, we can find out whether it is going to topple or whether it is going to slide. Okay. So you can imagine that we'll be doing things much more technically compared to what we've done in 9th, 10th, right? Because you haven't done this type of calculation at all. You understanding my point, people?
Yes, sir.
Okay. Okay, now just to complete this, after heat and thermodynamics, the next thing we will be doing is fluid mechanics, okay, and elasticity. So in this, we'll be studying things like elasticity of solids, of solid materials. Then we'll be studying surface tension, viscosity. So these are properties of fluids. Okay, then we'll also be studying about buoyant force and pressure in a fluid. And we'll also be studying steady flow, or what we were talking about earlier today, laminar flow, and from that something called Bernoulli's equation. Okay. And the final part of class 11th after this we'll be studying will be waves and sound. So again, something that we have seen in 9th, 10th, but in a lot more detail. Okay, so this time we will be looking at the equation of waves. Okay. We'll be looking at intensity, which is something like energy. Okay. We'll be looking at something called interference of waves. Again, a term that you might have heard earlier. Okay. And some more things like that. Okay. So this will be more or less your class 11 syllabus. Okay. Now the point is to even start our study of class 11, which starts with mechanics, which is going to start, actually it's going to start with kinematics, even before forces. Kinematics is the physics of motion. Okay. So even before we start this, we will have to learn a certain section called vectors, because a lot of physical quantities have direction as well as magnitude. Okay. So physical quantities can be divided into two categories. Some of them have direction, like force, okay, displacement, velocity, etc. Whereas some have only magnitude. Like mass, time, density, heat, okay, and so many more like this. Okay, so these quantities which have direction as well as magnitude, as you might have heard, these are called vectors. These are called vectors. Okay, and vectors have a different type of algebra. So that is called vector algebra. Okay, so for example, if I have a body on which I'm applying two forces, I'm applying one force of, let's say, 15 newtons like this, but I'm applying a second force of, let's say, 20 newtons like this, such that the angle between these two, suppose this angle is 45 degrees. Okay, so then from this, how do I calculate? So given the mass of the object, I should be able to calculate the acceleration of the object. Acceleration A should be the net force divided by the mass. Okay. Now what will be the net force? The net force is the vector sum of F1 and F2. So you can guess over here that vector sum will not be 70 newtons. Okay, it will be something less than that because there's some angle between them. It would have been 70 newtons if we were applying the force in this way. That F1 equal to 50 is acting like this, but F2 equal to 20 is acting in the same direction. In this case, the net force would have been 70 newtons. Okay, the sum of these two. But at the same time, if the forces were acting in the opposite direction, like F1 was acting like this, and F2 was acting like this, then the net force would have become how much? It would have become 30 newtons because they are opposing each other. So like that, in this case, because neither they are opposing nor they are parallel, so I know that the net force will neither be 70 newtons because they are not parallel, nor it will be 30 newtons because they are not opposite also. It will be something in between. So exactly how much it will be. So to learn that, we will learn vector algebra. Okay. So that is one of the topics we will start with in the next week. Okay. With that, I bring it to a conclusion for today's session. So what we are seeing here is that to even start our journey in physics, where we start with the basic things like force and velocity and acceleration, etc., in kinematics, in Newton's laws, and in mechanics in general, we need to be able to negotiate quantities like this, which have both magnitude and direction. We need to be able to add, for example, two forces which are at a certain angle, or subtract two displacements, where the displacements are in different directions. So how we add or subtract, or how we do other types of operations involving quantities which have both magnitude and direction, that comes under the topic of vector algebra. So one of the chapters we will be starting with in physics next week, that will be vector algebra. So many of you might have received your first module in physics, module 1 in physics. Many of you may not have received also. You will get the PDF of this very soon then. Okay, this is called Useful Mathematics of Physics. And that contains two things. It contains vectors, and it contains something called basic calculus. So don't worry about basic calculus. We will explain to you in the coming lectures what is basic calculus, but vectors is something that we will start with next week. Okay, so by next week, all of you will at least receive the PDF of this module if you don't have the physical copy. Okay, and you don't need to do any background reading or anything. When we start the lecture, we'll tell you what to read from the module subsequently and all that. So for your reference books, many of you have asked me over the text message. Right now, for the next 3 weeks, we will not be following other reference books. You'll be following only your lecture notes and your module. But 3 to 4 weeks from now, when we have covered a certain portion of vectors and calculus, then at that stage, we will have certain reference books.
Sir, can you once show the illustration of the model?
Can I show the
image of the module?
Yeah, I'll show you. So reference books, we will be giving you a list. Okay, a separate list will be sent to you. Okay, in 3 to 4 weeks time, when we finish a certain portion. Okay, so we are almost done with today's lecture. I will just show you I'll share the, this thing, the PDF of the module. Just give me a second. Okay, people, unfortunately, I don't have a PDF of module 1 right now with me in this laptop, but I have a copy of module 2. So I'm just showing you two for example. Okay, but very similar to this, there'll be a module 1, which you will receive very soon. Okay, a PDF like this. So module 2, for example, has Newton's laws of motion. Okay, so each module will have theory notes. Okay, then it will have exercises 1, 2, 3, 4 like this. Okay, it will have previous year JEE questions, but before that it will have the theory notes, and in the theory notes there will be a lot of solved examples. Okay, for example, there are illustrated examples during the theory part. Okay, then at the end of each significant part of theory, there will be some collection of illustrated examples also. Okay, and some small exercises like this. For example, this is combination of springs in Newton's laws. And then there will be exercises like this one. So when the theory portion is completed for a certain chapter in the module, at the end of it, it will start with exercise 1, which are basic level questions. Okay, then moving on to exercise 2 and 3, which will be JEE Mains and partly JEE Advanced level exercises. Then exercise 4 will be JEE Advanced type questions. And finally, after that, there will be the previous year JEE questions. Okay, so everything from A to Z will be catered to in the module, including the theory and exercises, which is why you don't actually need any reference books compulsorily. But for your own benefit, at a later stage, when we complete more and more chapters, it will help if you refer to some additional books for some additional practice and additional reading, and that list of those books will be sent to you. Okay. So hope you found today's lecture somewhat interesting, though we have not covered anything of the syllabus. Yes, people?
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay,
Yes.
so that's it for today's session, people. See you next week and wish you all the best. And next week we will be starting with vectors. Okay. So all the best.
Thank you,
Thanks
sir.
for
Excuse me,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Yeah, beta.
Can I request you to send the notes that you were doing right now on the group chat?
Yes, I will send the notes on the group. Okay.
Thank you so much.
Okay, I will be sending you a recording of the lecture once it is uploaded on our YouTube channel. Okay. Plus, I will be sending you a PDF document which will have all the notes of what we've discussed in class today. Okay. Of course, today our discussions were quite random. So, I mean, notes may not be that important. It's just if you want to refer yourself. But next lecture onwards, when we are doing a particular topic, the notes will be very important because systematically each and every theorem, every definition, everything will be there in the notes. So along with your module theory notes, your class notes will also be important for revision later. Okay. Okay, so that's it for today, people. Wish you all the best.
Bye, sir. Thank you.
Okay, bye.
Thank you, sir.
Bye.
Thank you.